It's another great day for Stat135. It's lecture 4, and today we're covering the method of moment estimator and its important property called consistency, which is convergence in probability of the estimator to the parameter itself. We begin with a review of the gamma distribution. So we say, for example, that x is gamma r lambda. So x could be the time until your rth alpha particle arrives. R is the rth alpha particle, and lambda is the rate of the alpha particle arriving in your Poisson process. We have a density given here with a variable part that you should learn to recognize. The expectation and the variance are given here. So the method of moment estimator, or we will affectionately call it MOM, is computed as follows. We first start by computing the first L moments. So I'm assuming here that my estimator has L components. So we compute the first L moments to get a system of equations, and the kth moment is the expectation of x to the k, which by definition is an integral involving theta. So to calculate the expectation, we need to know theta. So these moments here are functions of theta. And so, for example, if x is Poisson lambda, then L is 1, and the first moment is just lambda. If x is gamma, L is 2, and we can compute functions. We can write the moments as functions of r and lambda, as shown. So then we use algebra to invert the above system of equations. So in the Poisson case, that's very easy. And in the gamma case, it's also easy, but just a little bit more algebra. So in step 3, we insert into our system of equations here. We don't know what these moments are, but we can insert an unbiased estimator, the sample moment, which we'll call mu hat. So we insert that, and that looks just like this. So it's just like a bootstrap type of situation where we don't know the parameter, so we just stick in an estimator. So, for example, for the Poisson, this gives us that the MOM estimate is just the sample mean, and for gamma, it's these two functions of the first and second sample moments. And the most important thing is that these are things that you can calculate. So when I ask you to calculate a method of moment estimator and I give you some data, you should always give me a number. Now, a property of the MOM estimate that we're going to care about is called consistency. But first we need to cover some probability prerequisites. So let's start with Markov's inequality. Markov's inequality gives you an upper bound for the tail probability, assuming only that the random variable has an expectation and that it is non-negative. So let's look at an example where the sample mean, we're looking at the sample mean here, and we're going to use Markov's inequality to give an upper bound for this quantity here. Notice that the absolute value sign is a random variable, here non-negative random variable, and epsilon some positive constant. So we should be able to apply Markov, but we're going to rewrite the event by squaring both sides, which doesn't change the probability. And then by Markov, we see that this is just sigma squared over n epsilon squared, which is a quantity that goes to 0 as n goes to infinity. So we can notice that here. So what this says is that the probability that you're in the tails, right, so the absolute value of the sample mean minus mu being greater than epsilon means that you're in the tails. This is less than or equal to sigma squared over n epsilon squared. So the amount of area in the tails should decrease with n. So for example, I have two curves here. One is for n is 10, and the other, I didn't write, let me rewrite this. So this one, say, is n is 10, and the steeper one, let's say, is n is 20. Okay, so the n is 21 has less area in the tails. So now convergence and probability. The idea is that we have a sequence of random variables. They converge to a random variable x if for any epsilon the absolute value of the difference being greater than epsilon goes to 0 as n goes to infinity. So an example of this is the weak law of large numbers, which says that the sample mean goes to the population mean in probability. So here, when I write this, I'm thinking of mu as a random variable. It's just a constant random variable where it just has a single outcome with probability 1. And so we proved the weak law of large numbers above, right? So we saw that the probability that the absolute value of the sample mean minus mu greater than epsilon is sigma squared over, is less than sigma squared over epsilon squared n, which goes to 0 as n goes to infinity. So now the generalized weak law of large numbers is just an extension of the weak law of large numbers to higher moments. I won't actually prove this, but if you're really curious why this is true, then you can just Google this. I should put a P here. This is true, and so we showed it for the k is 1 case. And now what we're working towards is proving consistency, and we need to introduce the notion of a function being continuous. So recall that a function h is continuous if given a sequence of points a1, a2, and so on converging to a, then h of a1, h of a2, and so on converge to h of a. So just simple calculus or pre-calculus definition, but this actually applies to random variables. So we have a nice theorem. It says, suppose x1 to xn and so on converge in probability to x, and h is a continuous function, then h of x1, h of x2, and so on converges in probability to h of x. So now we're just a few lines away from showing consistency. So by definition, an estimator theta hat is of a parameter theta is consistent if theta hat converges to theta in probability. So we argue that mom is consistent. So we have that theta hat, that the sample moment converges to the kth moment by the generalized weak law of large numbers. And so if h is continuous, then the estimator, our estimator, which is a continuous function of our sample moments, converges in probability to theta, which is h of mu1 to mu l. So that's it. That proves consistency, and next time we will look at, I'll give you an example of an interesting example of computing a method of moment estimator, and we will start